Welcome to the course on computer design of electrical machines. We have a lecture 23, design of synchronous reluctance machine, part 1, with the outline of presentation with the introduction, motor comparison, application, equivalent circuit, design of synchronous reluctance motor, then numerical questions and references. So, coming to with the introduction, you can just see how your synchronous reluctance motor look like from inside, typically with the flux barriers on the starter winding is similar to like a induction motor or synchronous motor, but the rotor is with the flux barrier. So you can clearly see in the photograph how it look like. And normally these motors are nowadays run by variable frequency drive, as you can see the drive, shown on the side of it. So the rotors of synchronous reluctance motors are cheaper and lighter than rotors of induction machine and permanent synchronous machine. With the same size, the power factor of the synchronous is rather poor compared to the both induction motor and permanent synchronous motor. Efficiency of synchronous reluctance motor is much better than the induction motor and inferior, slightly inferior than the PMSM. The stator of synchronous reluctance motor and the inverter to supply them are identical to those of induction motor and permanent synchronous motor. So typically you can see how is a rotor of the synchronous reluctance look like, typically with the flux barrier, very special design which is only as an innovation as in a last decade only, with the material good partial load efficiency and the super premium efficiency, combination of benefits with the induction PM motor and service free, a wide speed range and high reliability due to the low winding and bearing temperature. And of course, the concept here of synchronous reluctance is that rotor is only cylindrical, cylinder pole. Stator winding is cylindrical, normally similar to conventional synchronous motor and induction motor, but the rotor is a cylinder pole with a special geometry. And this is the evolution history, how it has gone to synchronous reluctance motor with the typically starting in 1888, then 1923 with the typical kind of flux barrier, then it gone to 1960, 89, how it is really old with the, and then finally 1998, 2005, finally in 2010. So you can say, with the simple first A with the simple cylinder pole, then axial limited and transfer laminated and Kostenko, of course, original patent, AV synchronous servo motor, AV synchronous and drive package like. And you can just see how it look like as a comparison of synchronous motor and induction motor. You can say the synchronous motor is shown your smaller size, and below behind the image you can see of induction motor. So the advantage here is for same power is smaller motor, same size motor, higher power, and compared to induction motor outside, the innovative inside, an i3 compact design without compromising efficiency, then full range and verified package efficiency. And typically you can compare how look like your synchronous motor and synchronous reluctance motor, with the flux barrier. So very special design compared to induction motor like. So you can just see what is the benefit. You are able to reduce in synchronous motor losses up to 40%. As you can see, IA square losses which are completely eliminated. So you have only the stator copper losses and some other losses in synchronous. So left side is the induction motor, right side is your synchronous reluctance motor. And you clearly see the rotor flux barrier, which is very special design kind of flux barrier. And typically here also you can just see in induction motor you have I square rotor copper losses, then other losses I square losses, but in case of I4 synchronous motor you have only 60%. So the loss and I square loss. Of course, in case of your higher output power synchronous motor, these are reduced only by 10 to 20% like. So you can clearly see the efficiency versus power characteristic of induction motor and synchronous motor. So you will find a large gap in the lower rating, because induction motor does not provide the good efficiency and lower rating. So in lower rating, synchronous reluctance motor are becoming very popular. Because of this large high efficiency even at kind of partial load. So the basic concept of synchronous reluctance motor operating principle is based on the reluctance concept as shown in the figure with the flux barrier, and an anisotropic rotor is placed in a magnetic field with the defined direction and reluctance torque is produced. And this torque is due to the interaction of the non-uniform magnetic reluctance in both the Q axis of the anisotropic rotor and the magnetic field. The magnetic reluctance in the D axis direction is much lower than that in the Q axis direction. And the reluctance torque is produced to align the D axis of the rotor with the magnetic field. Therefore, the rotor rotates to an in position as shown in the figure. And you can clearly see what is the cross section A of anisotropic in place magnetic field. So rotor position A and rotor position B with the length to typically the magnetic field, in all the So the reluctance machine, synchronous machine or synchronous reluctance machine have a uniformly slotted stator core with a distributed almost pole pitch tau span coils winding connected in two split phase, 3 or more phases. The phases are fed with the sinusoidal current that produce basically a sinusoidally MF Fs equal to F1m cos omega 1 t minus pi upon tau into x. And typically you can say distributed winding instead of synchronous motor 3 phase 2p equal to 2 pole and 4 pole machines. How the typically flux barrier, and here typically two kind of geometry with the rotor concentric and the salient pole with the distributed. So they exhibit 2 PS poles per rotor geometry, and the poles is equal to the variable reluctance type showing the same number of poles 2p are equal to PS equal to 2p, and the variable reluctance rotor may be built in quite a feed configuration with the rotor regularly laminated and concentrated, distributed magnetic anisotropy. So with the axial laminations of pole throw 2p greater than 4 and the respectively maintaining the shaft 2p equal. So you can see how it is the flux barrier in axially laminated anisotropic rotor with throw shaft. So typically the development of rotor by removing the teeth from the rotor of a conventional induction motor, the rotor saliency can be achieved, and this saliency we can achieve maximum of the three. That's the method some people have used in cross section of in the evaluation. And then the rotor of ordinary salient pole synchronous motor without excitation winding. So saliency ratio is low, and the saliency ratio for this of rotor was reported equivalent to 3. Then the development typically rotor with flux barrier by adding the flux barrier in a non-magnetic material in the Q axis below the cage winding, the rotor was achieved. This rotor geometry will allow the motor to start direct online, and by removing the permagnet from the interior permanent motor, the flux barrier insulation is achieved, and the saliency ratio of these kind geometry has were reported 6 to 8. And in 1923, typically Kostoko investigated the aforementioned rotor geometry typically of this transversely limited anisotropy TLA construction, mainly due to faulty form of the rotor. To increase the torque, it is necessary to prevent as much as possible the formation of the transfer field, and to cut out the part of the rotor where the Q axis field will be maximum. In these rotor designs, some of the useful D axis flux are lost, and this is typically the cross section of axial laminated anisotropic rotor, ALA rotor. The laminations are probably shaped insulated to each by magnetically and electrically passive material, and stacks are concentrating through the pole holder to the concentric part of the where the shaft is connected. And here is the cross section of the TLA rotor with equal spaces between the equivalent rotor slots. So you can see the laminations are punched in the traditional way, and thin ribs are left to hold the rotor segment together. To achieve the anisotropy, there are ribs should be magnetically saturated, result in additional leakage component of the Q axis flux, and transversely limited anisotropic TLA rotor give the mechanical strength to the rotor stack as easy and cheap way, and the saliency ratio TLA has a lower saliency ratio than ALA. So multiple flux barriers making use of regular laminations proposed in 1950 has gained recent industrial acceptance by ABB up to power of 500 kilowatt in variable speed inverter fed drive. It has having 1.5 to 3% more efficiency than induction motor with the same stator, but the power factor is smaller, 8 to 10%. Segment load configuration retain only a historical. The axially laminated rotor is still considered less practical unless the performance is far more important than the initial cost and material pulse fabrication because of the stator to access current magnetic field space harming produce additional losses in the LA rotor, while the second objection has been solved by using the thin slits 3 to 4 per entire rotor axle length. The first objection still hampers its commercialization. So the rotor stack and lamination typically stampings, you can see how it look like this kind of construction, and then the rotor complete stack. So typical synchronous reluctance motor topology with a multiple flux barrier of anisotropic and with axial limited ALA rotor with the distributed 3-phase winding. So here it is a typically the kind of magnetic circuit. So two-pole equivalent magnetic circuit in the Q axis. Calculate the rotor segment magnetic potential Y1 and Y2 and the machine rotor and stator slotting. and then the 2-pole ALA rotor synchronous with the no throw soft, then the 6-slot 4-pole tooth wound coil TW suit synchronous mechanical action fan instead prototype, then the typically ALA rotor 2-pole 1.5 kilowatt 50 Hz FEM line in D axis and Q axis, then the typically here I have a 4-pole synchronous and PM assisted synchronous reluctance by FEM synchronous cross section area. Out really, I mean in the left side we have synchronous and right side we have a PM assisted synchronous reluctance model. So now coming to number of flux barriers. Number of flux barriers has significant effect on characteristic of synchronous reluctance motor. So during the design process, simulations have been done with different numbers of flux barriers in the rotor. The output torque tends to increase with the increase in number of flux barriers, and the torque will decrease with the increase in barriers. And the increase in torque is saturated as a flux barrier of 6. Hence, in the rotor design optimization, the minimum number of flux barriers has been set as 6. So here you can see number of flux barrier and the torque, how it is really the output torque and torque ripple. So you must have a torque with the flux barrier, the torque increases, output torque increases, and torque ripple reduces. Like so, at least with this you must have at least minimum number of 6 flux barriers. Like so, the effect of flux barrier variation over the inductance profile of an synchronous type prototype can be seen in the given figure. The Q-axis inductance LQ decreases until 4 layers, while the D-axis inductance increases till 6 layers, and as a result, difference LD-LQ which affects the torque has same value for the 6th layer to more. So that's the reason 6 layers supposed to be kind of optimum for this LD-LQ selections. Like, and these are the sample performance of synchronous for variable speed for different rating motors and different speed typically, like also compared to like induction motor. So induction synchronous motor measure and typically your synchronous reluctance motor calculated, like so it certainly have a, of course, current little larger, but losses much lower. As you can see, losses 1280 to 928 watt. Typically in the motor of 13.8 kilowatt or so. And the synchronous reluctance may be used in the line start constant speed machines. However, a cage had to be added on the rotor for asynchronous starting, as you see here. So higher efficiency in contemporary line start synchronous motor split phase and 3-phase synchronous has been vigorously pursued, especially with PM when Farad assisted induction motor, but keeping the starting current lower than 6.5 per inch. These are the typical standard for efficiency classification. Now coming to the non-symmetric cage is admitted producing additional torque pulsation during the asynchronous starting, but he used the rotor cross section area better than while leaving the room for the assisting common. The synchronous reluctance motor are in general provided with distributed winding in the stator to produce the higher magnetic anisotropy, and good results may be obtained with T upon jaw pole pitch to air gap more than 300 and Q equal to greater than 3 slot per pole per page. LD upon LQ can be up to greater than 20. And these are the typically possible rotor design with the simple cell pole, axially limited and transversely limited rotors. And then had and rotor with the axially transversely limited. So large magnetic asymmetry magnetization inductance differential LDM upon LQM in the two orthogonal D and Q axis is required for high competitive torque density Newton meter per kg or Newton meter per liter, while the high ratio LDM plus LSM plus LQM LM LD upon LQ is required for acceptable power factor than the wider constant power speed range. So first RS synchronous reluctance synchronous motor using cell and pole standard rotor pole exhibited low saliency LD upon LQ 1.8 2.5. However, rotor simplicity and resistance proved practical many in the low power, especially high speed application. So typically here unexcited conventional cell and pole synchronous machine are known as relatively small reluctance, torque and power factor. So small LD upon LQ ratio responsible for poor performance. So more advanced rotor configuration have been proposed to increase the saliency LD upon LQ and consequently the performance. And the most important configuration are the flux barrier rotor and the solid iron segmental rotor, as is shown here. So ratio LD upon LQ under moderate saturation content does not surpass 6/7, while the LDM longitude magnetization reduced by 20% with respect to its value for the uniform air gap. So distributing the anisotropy in the rotor with axial lamination packs separated by the insulation spaces or with the transverse lamination produce higher LDM upon LQM and low harmonic content in the air gap flux distribution, and the ratio LDM upon LM, where the LM is the magnetizing inductance of the corresponding induction motor with the same air gap initiator and kept as 0.96 with the smaller harmonics in air gap flux distribution along the axis, and it's worthwhile finding if and when synchronous reluctance may be equal or even surpass induction motor or PM motor in performance. So the advantages are higher efficiency, no conductor loss in the rotor, generate heat, less heat loss, less heat, less maintenance due to the lower bearing temperature, can be used in variable speed drive, rotor synchronicity, granting a more accurate speed control, no rotor slip, high torque density, and lower rotor inertia means faster rotor diameter. Disadvantage, slightly lower power factor for potential increase in water requirement, and of course in not widely manufactured. Now coming to motor comparison. As the stator is considered the same for induction motor, PMSM, and synchronous reluctance are the comparison based on torque capability. For the same stator current correspond to ID and IQ. The synchronous reluctance motor torque equal to surpass the induction motor torque. So LQM is less than LRQ, or LDM is greater than LM. So LM is the magnetizing index of induction motor, LRQ is the induction motor leakage reactance, LDM is the longitude magnetization inductance, and LQM is the transverse inductance. So peak torque of PMSM is limited to avoid the demagnetization of PMM. So it is smaller than the peak torque, short duration of induction motor and synchronous motor for the same stator and rotor flux linkage. Typically the loss oblique torque ratio. So for a given IQ and given ID for induction motor and synchronous motor, the same torque can be obtained. The lowest winding losses occur in PMSM and higher in induction motor. Induction motor, the rotor winding losses increases with IQ and are constantly higher than synchronous motor. So concerning the minimum loss of torque condition, it is noted that the corresponding torque is small both in induction motor and synchronous motor. So minimum electric losses torque ratio, high torque occurs especially in at high speed. So kilowatt to kV ratio for power factor for maximum torque is 0.702 for PMS and very close to the value of induction motor synchronous. The good power factor occurs only in induction motor and synchronous motor, has a value close to LS upon LS equal to LD upon LQ, where LS is the total inductance of the induction motor. Now torque tangent speed is very important for fast response speed and position response in modern drive, and at low speed the ID is kept constant, non-zero for induction motor and synchronous motor, and 0 for PMSM in order to provide the IQ and thus fast torque response. It is possible to adopt the strategy of constant current angle maximum torque ID upon IQ equal to LD upon LQ, which is applicable for wide speed range. The torque response is faster at lower speed for induction motor and slow for PMSM. Now coming to application of this synchronous reluctance motor are in metering pump, auxiliary time mechanism, wrapping and folding machines, proportioning devices or on pumps and conveyor, synthetic fiber manufacturing equipment, process continuous sheet and or film material. So typically you can see how it is like a metering pump, the synchronous reluctance motor. Then typically the images of synchronous motor with the wrapping and folding machines. Then the box wrapping machine, the tray sinking wrapping machine with the variable speed, and of course synchronous reluctance motor give a higher efficiency. Paper folding machine, then metering folding machine, then the synthetic fiber manufacturing equipment, then pressure booster pump, then the pump and conveyors, then the electric vehicle. Then coming to equivalent circuit, we have equivalent circuit according to the synchronous reference frame, the direct axis, where we have of course resistance at synchronous reference speed, the speed omega m into lambda sqls and then lambda md, that is direct axis, and there is a quadrature axis equivalent circuit of the synchronous reluctance motor for both axes with the VD and EQ. And this is the phasor diagram of D and Q axis for the typically of ID and IQ axis, and then the typically the flux of along with the A axis, the angle corresponding to theta, and the with respect to the D axis and Q axis angle is theta plus alpha I. So from this vectorgram, the load angle can be computed as delta equal to tan inverse lambda SQ upon lambda SD equal to tan inverse LD upon LD LQIQ divided by LDID equal to tan inverse rho ID upon IQ upon ID, where eta is the saliency ratio and alpha equal to tan inverse IQ upon ID. Thus the load angle is given by delta equal to tan inverse 1 upon eta tan alpha I. Both delta and alpha have effect on machine performance as well as saliency ratio. So from the interaction between the hysteretic current vector and the flux linkage factor, the electromagnetic torque is T equal to 3 by 2 P lambda s into Is, where P is the number of pole pairs, so tau equal to 3 by 2 P in bracket lambda SD IQ minus lambda S, your SQID equal to 3 by 2 lambda SD upon LQ and minus lambda LD equal to 3 by 2 lambda SD divided by 1 upon LD minus 1 upon LQ upon minus LD by substituting lambda is equal to Vs upon omega. The electromagnetic torque can be expressed as function of motor saliency. The amplitude of a stator vector Ps and load angle T equal to 3 by 2 P lambda square LD minus LQ upon LD LQ into cos delta into sin delta equal to 3 by 2 P lambda square LD minus LQ 2 lambda sin 2 delta, or 3 by 2 P V square LD minus LQ 2 omega square LD LQ to sin 2 delta. So electromagnetic torque can be expressed as a function of the motor saliency. The amplitude of hysteretic current displaced vector is and IL T equal to 3 by 2 P LD minus LQ into IDIQ, or equal to 3 by 2 P by 2 into LD minus LQ IS square sin 2 alpha I. And this is the characteristic torque versus load angle. You can see for the different saliency ratio, typically how it is really varying, the maximum torque at 45-degree angle in per Newton. And this is the current angle versus the torque, with the different angle. So you can see at around 90-degree angle, you will just finding the maximum torque. And similarly for torque versus current angle for typical constant hysteretic flux. And this is typically a current angle versus torque, which called MTPA. Coming to power factor computation, the power factor cos phi can be computed as cos phi equal to cos pi by 2 minus alpha my plus delta. By neglecting the hysteresis losses and iron losses, it is possible to access the balanced electromechanical energy conversion 3 by 2 EBS cos phi equal to T omega I, and where lambda is equal to under root lambda D square plus lambda Q, I is equal to ID square plus IQ square, cos phi equal to LD minus LQ into IDIQ under root divided by under root LD ID square plus LQ IQ square multiply under root ID square plus IQ square. So cos phi equal to LD multiplied eta minus 1 into LD IDLD divided by LD IQ under root LD ID upon LQ IQ square plus 1 under root ID square plus IQ square equal to eta minus this ID upon under root ID square IQ square divided by under root eta upon del alpha I square plus 1, or equal to eta minus 1 cos alpha under root eta square cos square sin square alpha plus 1, and that is equal to alpha eta minus cos alpha root eta square sin 1 upon sin alpha square plus 1 upon sin I equal to eta minus sin 2 alpha divided by 2 tan alpha plus 2 eta cot alpha. And this is power factor versus current angle, how it is varying typically. So maximum power factor you can get typically order of, it depends on saliency ratio, so you can get order of, at the 10 the value of around 0.85. This with the typically saliency ratio with the power factor, you are able to get 0.8 order of 8 with the saliency ratio of around typically about value of 8 like also. And this is the typically operating limits and work flow with the variation of IDIQ, which you call it MTPA and MTPV, maximum volt per turn and maximum torque per ampere. And typically so coming to the design of synchronous reluctance motor, the design of synchronous reluctance machine refers to electromagnetic, thermal and mechanical aspect. So unlike other electric motors, the electromagnetic design has some notable peculiarities and very much depends on applications. So in the case of servo drive, a quick response with the wide range for position control application is required. In the application of power drive for medium, tens of kilowatt, or higher power drive, hundreds of kilowatt with moderate speed range, line start constant voltage and constant frequency is another configuration with mandatory cage, distributed winding, distributed and isotopic rotor. So coming to servo drive motor design aspect, so initial data typically tangent, short time, torque is considered higher than the continuous torque and is used primarily for fast speed acceleration, deacceleration and speed reversal. and the magnetic circuit should be designed for tangent torque, while the electric circuit requirement should be designed for continuous torque requirement. So the base speed omega b and the maximum speed omega r maximum are also important influence on the design. In general, the ideal acceleration time Ta is defined in the base speed T equal to omega b j upon p1 t ek, where peak tangent torque Tk is available up to the base speed of omega b. So now coming to typically initial data. Above base speed, the flux weakening is performed up to maximum speed in the very fast response time. The base speed is equal to the maximum speed, and also as the motors are to be fed through PWM voltage source inverter, the input DC voltage is required to be known. For star connection, maximum phase voltage for synchronous motor known as PVH, VRPH equal to root 2 V 0 by pi into KVP, where KVP is 0.921. So typically the factor KVP accounts for limitations of available maximum voltage through the PWM. For a particular requirement, the initial data for design are given here. Peak tangent torque, if we take T peak 40 Newton, then base speed typically 3600 rpm. Ideal acceleration time to base speed is 24 milliseconds. Number of pole pairs to 1. DC input voltage 300 volt. Then maximum speed for 3600. Peak torque at speed T Pk dash equal to and continuous at base speed 10 Newton meter and continuous torque at maximum speed Tm equal to Bk. So now coming to servo drive design as the rotor diameter and stack length. So the key constraint for rotor diameter computation is the acceleration time Ta. So Ta equal to omega b j upon p1 Tk. Putting value j omega b upon p1 divided by 3 by 2 p1 ld minus lq idk, and iqk and id upon iq equal to ld upon lq. So idk represent the maximum value of id for which the degree of saturation present is still moderate, and thus the air gap density B1 dm corresponding to idk is defined. The relation between idk and the phase current is idk, the rms equal to idk upon by root 2, and typically the expression for B1 dm is equal to B1 dm is 3 root 2 V0 and 1 kW1 k id upon pi P1 G Kc in bracket 1 plus Ks into Kdm, that is around 0.6 to 0.66 Tesla. Corresponding air gap flux B1 cam is idq is B1 qm equal to B1 dm kq m1 into id iqd qk divided by kdm1 idk equal to B1 dm kqm ld upon kdm1 and lq, where G is the air gap, Kc is the Carter coefficient, Ks is the saturation, N1 is the turns per phase, and Kw1 is the winding factor. So now Kdm1 and Qqm1 depend essentially on T upon G. We may choose this ratio to provide saliency of ld upon Q. So for example, T upon G equal to 330 and ld equal to Ls, and value of ld upon lq15 is obtained, and you can just see the how the Kdm and Q the pole pitch and Kqm the pole pitch varies like. So the now moment of inertia is approximately J equal to mr square by 2, that is pi dr square by e power 4 by 32 into L into beta rotor, where L is the stack length of rotor, dr is the rotor diameter, b rotor is the equivalent specific weight. So to first approximation for the two pole rotor which have shaft ends, the specific weight may be assumed equal to the silicon lamination, e rotor equal to 7.6 into 10 power 3 kg per meter cube. So now also LDM equal to LM into KDM. So where KDM is 0.97 and top on G330. So top TP upon tau equal to 0.66. LM is the magnetizing of machine with the uniform air gap. So LM equal to 6 mu0 tau LM L N1 KW1 square divided by pi square K1 P1 G Kc into bracket 1 plus Ks. From these equations, dr square equal to 8 pi in bracket KDM minus KQM BD1 square Kc 1 plus Ks divided by mu0 LD upon LQ upon LD into B rotor into KDM square into P1 T upon omega B T upon tau. Putting the value, it comes 5.6955 into 10 power minus 3, and from which you get the d r equal to 7.54 into 10 power minus 2 meter. So rotor diameter Tr equal to 7.54 into 10 power 2 meter or 7.54 centimeter. So in 9, the Carter and saturation coefficient are assigned with the initial value K is equal to 1.23 and K is equal to 0.4. Later slight adjustment may be introduced, and the pole pitch tau equal to pi dr upon 2, that comes 0.0 0.11837 meter, and air gap is equal to 5 upon 330, that is 0.35 millimeter. So stack length is computed from this, may be taken the value of TA. So from this equation, J equal to pi drr upon 32 L into B rotor. So L equal to 0.1056 meter. The rotor diameter and top P on T are known. So in order to complete the rotor magnetic design, the axial lamination thickness BTR 0.38 millimeter and insulation layer BSR equal to 0.6 BTR, that is 0.255 millimeter required. So you can just see how it look like a typically stack length, L equal to 0.139 and with the thickness of BTR, axial lamination HR. So now coming to stator design, the stator design refer to the magnetic and electric circuit design. So let's double layer winding with the Q equal to 4 slot per pole per phase and soldered coil of Y upon tau equal to 10 upon 12. The winding factor Kw1 is Kw1 sin pi by 6 Q pi by 6 into Q, that is sin pi upon tau into pi by 2. Putting a value, it comes 0.925 and number of turns per phase is N1 equal to P1 Q Ns. Ns is the number of conductor per slot. So from this, Ns into IDS RMS equal to V1 pi D, G1 Kc 1 plus Ks upon 3 under root 2 V0 P1 Q Kw1 Kdm. Putting a value, it comes 65.5 ampere turns. On other hand, NSID equal to, putting a value in NSID into LD upon LQ, that comes 982.5 ampere turns. And total ampere turns per slot, NSIK is under NSID square plus NSIQ square. So putting value 9, it comes 985 ampere turns. And peak to continuous torque ratio, Tk upon Tm, that is 4 IDK upon IQK upon IDR IQR, and or IDK square LD upon LQ into IDR square under root LD upon LQ, and that is IDR under root LD upon LQ. So IDR equal to IDQ into 0.94. So IQR equal to IQK 1 upon 4 into this. So it comes 0.254 into IQK. Now strategy choosing the rated current density, J equal to 5.75 ampere per meter. Current density corresponding to maximum current, IK equal to 5, it comes 22.6 ampere per meter square. The useful plot cross section area is AS equal to N IK upon JK into K. So it comes 87.168 millimeter square, where the K fill equal to 0.5 is the slot filling factor. Now in order to compute the slot geometry, one has to determine the maximum air gap flux density B1 GK. B1 GK equal to B1 dm square plus B1 QM square, or B1 dm under root 1 plus KDM 1 KQM1 LD upon KDM1 into LQ, and putting KQM1 equal to 0.0323, KDM 1.72 and silency so 15. So B1 GK putting value it comes 0.738 Tesla. And the stator slot per pole, pole pitch toss equal to T upon 3Q, so it comes like 9.8648 10 power minus 3 meter, and adopting an average tooth flux density BTS 1.5 Tesla and plot with BTS equal to BT 1 J into toss upon BTS, the value it comes 4.853 into 10 power minus 3 meter. And the stator slot base width BS1 equal to BS1 equal to pi dr plus 0.006 upon 6 PQ minus BTS. Putting value it comes to 5.79 millimeter, and use your slot cross section as JS equal to BS1 plus BS2 HS by 2, where BS2 equal to pi DRR 0.006 by 2 HS upon 6 PQ minus BTS, and putting HS equal to 13 meter, we obtain BS2 equal to typically 9.2 10 power minus 3 meter, and AS equal to 97.44 or 80 greater than 87.89 meter square. So the slot opening is taken as BS equal to 2.5 millimeter, and the slot core height HCH equal to SCH with 1 GKTS top on pi into BCS, and putting value comes 21.4 into 10 power minus 3 or 21 millimeter as shown in the in the figure. Now the typical parameters expression. The motor parameters are the phase resistance RS, leakage reactance L sigma S, and magnetizing into LDM LQ. Leakage inductance expression is L sigma M equal to mu0 NS P1Q upon P1Q, lambda S plus lambda Z plus lambda F into L. So lambda S is slot permeance, lambda Z is the differential permeance, lambda F is the end coil permeance. So where the expression for lambda S, HS upon 3 B1 plus 2H2 BS1 plus BSS plus BH1 BSS, putting value it comes 1.63, Similarly, lambda z 5g upon 5 bss plus 4g, that comes 0.12588, and then the end connection LF is approximately, so LF is by d tau by comes 0.1858, and lambda f computing value 0.34 q upon L in bracket LF minus 0.64 tau, value it comes 1.41722, and consequently L sigma me, putting the value of all the mu 2 mu 0 and h p1 q square upon p1 q lambda s plus lambda z plus lambda f into L. So putting value it comes like 3.366 into 10 power minus 6 ns square. Similarly, phase resistance RS equal to rho 120 LC p1 q s ns square jk upon ns lik. The length of static coil is LC equal to 2L plus LF. So putting value is 0.6 meter, and P1G 2.35 into 10 power minus 8 ohm per, and JK 22.6 ampere per meter, and SK 8985 ampere turns. So RS comes, putting a value, it comes 1.31607 10 power minus 3 ns square. Magnetizing inductance LDM LMQM LQM LMKQM. So LM here calculated 6 mu 0 tau L P1 Q ns kW square divided by 2 pi P1 K G Kc 1 plus Ks, and the Carter coefficient Kc equal to Kc1 Kc2. Kc1 is 1 upon 1 minus gamma G upon tau s, and where gamma 1 Bss upon G square upon 5 plus Bss Gs comes 4.2, Kcs comes 1.17512, and Kc2 comes similarly 1.0522. So Lm comes, putting a value 22.117 into 10 power minus ns square. So LDM equal to Lm kdm. So it comes 2.105 into 10 power minus ns square, and LQM is Lm, it comes 7.01 into 10 power minus ns square. So now LSQ is 3.333668 into 10 power minus ns square, which is less than LQM 1.01 10 power minus ns square. So LD upon LQ, putting value it comes like typical 20.6. This is the value more than the certain value of 15. So now coming to number of turns per slot ns. So the vector diagram shows figure the peak torque, Tk, base speed, omega b equal to maximum speed omega r, yield the equation. So V dk equal to minus omega r max LD, sorry LQ IQ plus RS ID, and VQ equal to omega r max LD IDK plus RS IQ K, and VSK equal to VD square plus VDK square plus VQ square, and VSK is the maximum phase voltage, and fundamental RMS equal to VSK equal to root 2 V0 upon pi into KW, root 2 300 upon pi into 0.98, that is 132.588, and VDK, I mean keeping the value of this, so it come minus 3.75377 ns, and VQ comes 6.57 1.7 ns. So number of turns per slot is ns equal to 17.519, putting the value of this. So we can take ns equal to 18, 2-layer winding, and then the voltage VSK comes 136.227 volt, and to calculate the voltage required for continuous torque, omega equal to omega LD ID equal to IDK into 0.94, IQ equal to 1. So it comes LD equal to 1 3 into ns square, it comes 0.06927 or 69.27 millihenry, and LQ comes like your 3.36 millihenry, and RS comes typically putting a value 0.426 ohm, and peak current IK becomes 54.722 ampere, and the number of turns per slot ns equal to peak current density TP equal to TK by 4. So ID equal to IQK square plus ID square, putting a value comes like typically 14.33 ampere, and the continuous current components are ID equal to 3.54 ampere and IQ equal to 13.87. Next slot voltage component VDK equal to, it comes to 16.56 volt, and VQK comes 99.34 volt. And now number of turns per slot per turn, so Vs equal to Vd square plus Vq square, it comes 100.71 volt, and Tm comes 3P1 LD minus LQ ID IQ, it comes 9.8182 Newton meter, and instead of diameter DC0 10 by JC 5.5 ampere per meter continuous current. So DCO equal to 1/4 upon pi AC0, where AC0 is 1 upon I upon JC, that 2.492 meter square. So DCO comes about 1.8 millimeter. Now coming to as the motor geometry is complete, the magnetization characteristic computed, and Ks is evaluated. Whole process is carried out until the Ks value converges. If the ideal acceleration time is needed to reduce further, the rotor diameter will decrease as the air gap reduces. Air gap reduction leads to increase of Carter coefficient Kc and Ks in the kind of compensation. The low typically ideal acceleration time, the high peak to continuous torque is also a main asset of synchronous reluctance motor. Coming to numerical problems. Numerical 1, determine the rated armature current stator diameter effective stator length of 15 kilowatt for 15 3-phase 2-pole 3000 star connector synchronous reluctance motor. The product and eta cos phi at the rated load should be 0.9 and ratio of pole length to pole pitch is 1.5. Assume the winding factor 0.96, Am equal to 28,500 ampere per meter, flux density Pm equal to 0.75 Tesla, and output coefficient 101.262 10 power minus 3. Coming to solution, and eta cos phi is given 0.9, L upon tau given 1.5, Bm is given 0.75 Tesla, Kw 0.96, Am equal to 28,500 ampere per meter. Now coming to d square L Kw upon n cos phi into eta p into ns. So putting value ns equal to 50 rps, sigma p equal to 101.262 into 10 power 3. So d square L comes from here 0.003291 meter cube. L upon tau is given 1.5. This gives L equal to 2.3 d. So d from this calculation it comes d equal to 0.1117 meter and L comes to 0.263 meter and Ia comes P upon 3b comes 13.386 ampere. Now numerical 2, a 3-phase 415 volt 50 Hz 4-pole star connected single reluctance motor ID xt equal to 45 ohm and x equal to 10 ohm and the neglect resistance. The motor rated torque 10 meter. Calculate the reference ID component of hysteresis. So ID is given, xt is given 45, xq is given 10 ohm, then LD 0.143 Henry per phase and LQ 0.0318 per phase. The rated torque is 10 Newton meter. So now coming to solution, T 3/2 P by 2 LD minus LQ IDIQ. Then IDIQ comes 30 and V equal to 1 to U and LD square plus LQ IQ square. So substituting this IQ in this, so ID comes 5.178 and IQ comes 5.79. Now numerical 3, calculate the maximum flux density of in 3-phase 415 3000 rpm synchronous reluctance motor if motor has x equal to 45 ohm per phase and x equal to 10 ohm per phase and neglect resistance. Assume the d excess flux density 0.6. Let the ratio kdn equal to 30. So xt equal to 45, lq equal to 10 and ld 0.143 Henry per phase and lq equal to 0.0318 Henry per phase. So kdm 1 upon kqm 30. So maximum flux density is given expression here b1k vd1 square plus vq1 square or b1 square under root 1 plus kqm ld upon I to aq. So putting the value it comes 0.64 Tesla. And these are the references from which this material is prepared. Exclusive book, couple of exclusive book is for on synchronous reluctance motor, and thank you.